Hello, everybody. In this video lesson, we are going to be learning about combinations and how they differ from permutations. So there's a bit of motivation. We're going to get this problem here. We've got four people, Andrew, Ben, Corey, and Denise. They're all running for positions on their student council. So you guys can do this using our current tools. Maybe you want to do this in pause video. How many ways could these four students fill the positions of president, vice president, and secretary? So those are three specific positions. Take a moment and do that, or you can follow along with me. So we know two ways to set this up currently. We could set up a fundamental counting principle calculation, president, vice president, secretary. 4 times 3 times 2. That gives you 24 different ways they could fill the positions. But we also know that we could just use permutations because of our four friends. We are arranging 3 of them in a specific position. That also gives you 24. Same thing. Now in part B, we're asking, so in how many ways could these same students form a committee of three members? So a committee, it doesn't matter which order the students are in. So our four friends are, we'll call them A, B, C, and D for their names, Andrew, Ben, Corey, and Denise. And so how many groups of 3 can you make? So for example, ABC would be one group, one committee, but ACB, even though it's a different order, so maybe that's A as president, B as vice president, C as secretary, A as president, C as vice president, B as secretary. If we're just talking about a committee, those are the same committee. And so ACB isn't actually a new committee. It's the same. So we're looking for how many different groups of 3 people can we make here, but the order doesn't matter. So if you want to take a moment and think about how many different committees you can make, you can pause the video and then unpause when you're ready. But it turns out there's 3 more. ABD, you can leave C out. ACD, you can leave B out. And then BCD. If you think about it, those are the only 4 different committees that could be made. So we had, in the previous question, 24 different groups of 3 if the order mattered, and then 4 groups of 3 if the order didn't matter. If we think about what factor they're off by, well, the first answer, part A, was 24. So the 24 came when order mattered, right? The 4 groups of 3 came when order didn't matter. And 24 divided by 4 equals 6. 6 actually has a lot of relevance to this problem because 6 is the number of ways to arrange 3 people, right? That's 3 factorial. So that's very significant to us because today we want to determine a way that we can determine the number of groups we can make of, say, R objects from N objects, and when order doesn't matter. So here's the key idea. So here we're selecting a group of R objects from N objects. Again, order doesn't matter. It's like forming a committee. To get the number of permutations, what we normally do, well, I hope you would agree anyway, is that the number of permutations is the number of groups. So like you take a group, right, and then arrange it and then multiply by how many different times it can be arranged. So number of ways to arrange each group. So this is how you would get the number of permutations. Like, let's just think why this makes sense, right? So how many different ways can you arrange ABC, like specific arrangements? Well, you take, ABC is one group of letters, and then you multiply that by 3 factorial ways to arrange ABC. And then you take this guy and you multiply by 3 factorial. And this guy by 3 factorial. BCD by 3 factorial. That'll give you all the different ways to arrange 3 objects from 4. And so that's where we get this calculation from. This is just the number of possible groups. And then for each group of 3, there was 3 factorial ways to arrange them. So that's what we have. That's what we have here. Your number of different permutations is the number of groups times the number of ways to arrange each group. If you rearrange that to get the number of possible groups when order doesn't matter, you take the number of permutations and you divide by the number of ways to arrange. That's just rearranging what we had above. Now, guys, if you think about this, we actually know how to calculate both of those things. We know how to get number of permutations. That's NPR. We know how to arrange our objects. That would be R factorial. So this actually gives us a calculation, a way to calculate the number of possible combinations or groups. Again, so this is connecting to the previous slide. This is like the number of groups where order doesn't matter. We're going to call this NCR, combinations, where order does not matter. And the way we get that using the previous slide is the number of different permutations, which is, we know, is calculated by NPR. And the ways to arrange those R objects that you select is R factorial. This is a formula to calculate NCR. If we plug in our formula for permutations in terms of factorials, remember permutations, NPR was n factorial over n minus r factorial. The number of combinations is therefore n factorial over n minus r factorial. That's NPR. We're also dividing by r factorial. So this gives you a formula to calculate the number of possible groups of R objects from N where order doesn't matter. Like permutations, there are other ways to denote this. So another common way is to write that as CNR. You may also see this notation where you have 2 brackets and stack N and R vertically. That also means NCR. They all mean the same thing. So let's get used to this new formula, and also you guys will be using this feature on your calculator now. Let's just do a couple easy examples. So we're going to do 10C8. We also might word this as 10 choose 8 sometimes, because we're just choosing 8 of the 10 objects. And again, the order doesn't matter. So using the formula we developed earlier, that would be 10 factorial over 10 minus 8 is 2 factorial. And then R in this case is 8 factorial. And you'll notice the 2 factorials on the bottom will always add up to the top. And at this point, you can now evaluate that. You can do that calculation using factorials in your calculator, but I really would like you to make sure you find that combinations button, NCR, and verify that you get 45. There are 45 ways to select 8 objects from 10 if the order doesn't matter. Let's do 24C1. Maybe you want to pause the video, try setting this up by hand, see what you get, verify in a calculator. Or you can follow along with me right now. So using our formula, this would be 24 factorial. 24 minus 21 is 3 factorial, and then 21 factorial. This is a bit larger. You can verify it on your own, but that gives us 2,024 different ways to select 21 objects from 24. So the big idea is that combinations are related to permutations. The difference is you're dividing by the number of ways to arrange the objects you select, which in this case was 8 objects selected, 8 factorial, 21 objects selected, 21 factorial. The main difference, so this is something that we have to drill into our heads, is with permutations, order matters. And with combinations, order doesn't matter. So as you are doing problems moving forward, you have to think about, hey, does the order matter in my question or not? If order matters, I should be using permutations. If order doesn't matter, I should be using combinations. So let's do some examples with combinations where order doesn't matter. So here's our first example. Not many of these are open anymore, but I know that where I went to school in Waterloo, we had a Mongolian grill. It was one of my favorite places to go eat with my friends, because you would just go, put all these raw ingredients into a bowl that you want to create your own bowl, and then they would put this bowl on a huge stone like stove top and just like cook it right in front of you. You were advised to only have one type of raw meat, but we usually, disregarded that and tried to one up each other. But let's say, against your friend's advice, you put 3 different types of meat into a bowl at the Mongolian grill, and there's 10 types of meat to choose from. How many different bowls could you make? Well, I hope you guys would all agree, when you put all these ingredients into a bowl, they get mixed around and cooked. Like, it doesn't matter which one you put in first. The order doesn't matter here. So in part A, we're looking for the number of ways to choose 3 meats from 10 where the order doesn't matter. And of course, that's just 10C3. You can do that on your calculator and verify. You get 120. So that's the number of different bowls I can make, at least as far as meat goes. If I choose 3, what if I chose 4 meats? Well, it would be 10 choose 4, and you guys can do that. And again, at this point, we're moving towards just using our calculators for these kinds of questions. You should get 210. So lots of different bowls you can make. What I'd actually like you to do right now, before we go on to the next phase of this problem, is just give it a try on your calculator. What 10 choose 0 is, what 10 choose 1 is, also 10 choose 7. I have a specific reason for each of these. 10 choose 6 and 10 choose 10. If you could evaluate those 5 and maybe pause, evaluate those 5, and maybe even think about why you got the results you did. Come back and we'll talk about the results. So I'll assume right now that you've done that. 10 choose 0 is 1. 10 choose 10 is also 1. So if we think about it this way, 10 choose 10 is saying, how many ways can I put all 10 types of meat into my bowl? Well, there's only one way to do that. You're choosing all of them. 10 choose 0 is kind of similar. It's like asking, well, how many ways can you pick 0 of the meats to put in your bowl? Well, there's just one way to do that. You just don't put meat in there. You could also think of it as, how many ways can you choose no meats to be left out? It's the same as 10C10. 10 choose 1 is 10, which makes sense too, right? Like, there's 10 meats to choose from. How many ways can you choose one of them to be in your bowl? Well, there's 10. As just an aside, even one more, 10 choose 9, if you try that, will also give you 10. There's some symmetry there. That makes a lot of sense, actually, because if you're choosing 9 meats, then you're leaving 1 out. And so the number of ways to choose 9 meats should be the same as the number of ways to leave 1 of them out. It gives you 10 both ways. On the same logic, the number of ways to choose 3 meats from 10 is 120. The number of ways to leave 3 meats from 10 or to take 7 is also 120. And 10C6, you will notice, is 210 as well. So that's really interesting, the symmetry with combinations. Let's move on. What about in this example here? Okay, so we're not just putting meat into these bowls. We're going to have some vegetables too. So let's say they have 8 different types of vegetables to choose from. And we're going to put 4 types of vegetables in, as well as 3 kinds of meat. How many bowls could we make? So we're kind of ramping things up here. We're going to use combinations, but also the fundamental counting principle as well. So we got to think about, well, how many ways can I choose my meat? And how many ways can I choose my veggies? Well, we already talked about earlier, the number of ways to choose 3 meats from 10 would be 10C3. And of our 8 veggies, we're choosing 4. There's 10 choose 3 ways to get meat and 8 choose 4 ways to get veggies. The fundamental counting principle says to get the number of possible bowls with 3 meats and 4 veggies, you multiply those 2 results together. So you can give that a try. I'm just doing it here where I am as well. 10 choose 3 times 8 choose 4, and that's about 8,400 different bowls you can make with 3 meats and 4 vegetables. So we can combine tools here. We combine combinations with the fundamental counting principle here. Why don't you try this question? It's along the same lines as the previous one. We have a students' council with 8 boys and 10 girls, and we're making a committee of 6 with 3 of each, 3 boys and 10 girls. How many committees can be created? So committees, big keyword, work well with combinations, because in a committee, it doesn't matter who's chosen first. When you see committee, you should be thinking right away combinations, not permutations. When they have specific positions like president, vice president, etc., then you'd be using permutations. Here you're using combinations. If you want to pause the video and try this question on your own, please do. Otherwise, follow along. So we have to choose the 3 boys, and then we have to choose the 3 girls. So how many ways can we choose the 3 boys? Well, there's 8 boys, and we're choosing 3 of them. Again, it's a committee, or does it matter? To choose the girls, there's 10 girls, and we're choosing 3 of them. There's 10 C3 ways to choose our 3 girls. And that's it. We will multiply these 2 results together. Apply the FCP. So 8 choose 3 times 10 choose 3. So you should be trying this too on your own. I just did it right now, and I got 6,720 different committees. All right, let's move forward. Take a moment. Maybe you want to pause and think about this. Why is the name combination locks misleading? Most of us have used a combination lock, and maybe you even use one right now. Is there a better name for combination locks? Well, there is, because all of us know from opening a lock, when you do a combination lock, if you put your 3 numbers in the wrong order, the lock will not open. But when we use combinations in the organized counting sense, that means order doesn't matter. So a better name would be a permutation lock, because order matters with permutations, right? Order matters with permutations. These locks should be called permutation locks. So that's an interesting conversation starter. Sharing some knowledge with your friends regarding organized counting. I personally still call them combination locks, and I think that's just so ingrained in our language. But it is an interesting idea that technically they are permutation locks, because order matters. All right, let's do some more examples, just kind of broaden our horizons, the types of problems we can do. So here we have 10 members of a business board, and they're getting together for a meeting. And just like with a lot of meetings, everyone's going to shake each other's hand. So everybody wants to shake everyone else's hand, and you're not going to shake the same person's hand twice. So if everybody needs to shake hands, how many handshakes take place? So on the surface, it may not look like a problem that involves combinations, but it actually does. Can you think about my class in school is also doing this, so I have this discussed with your classmates. But there is a way to frame this in terms of combinations. Can you think about it? Oh, you can pause the video and unpause when you're ready. But we can actually go directly to our answer here, because if you think about it, a handshake is like a group of 2 people, and it doesn't matter whether person A initiates and shakes person B's hand, or vice versa, B shakes A's hand. The hands get shook no matter what. So it's like from 10 members, how many groups of 2 can we make to do a handshake? And again, the order does not matter here. And it turns out there were 45 handshakes would take place. So that's an interesting problem I always like to do because you can frame it nice and easy in terms of combinations. It's pretty cool. 45 handshakes. One more example for you guys to try. So there's 7 dots at the bottom right of your screen here. Let's say they represent the location of cabins in a snowy area. Something rather important to this question is that no 3 cabins lie on a straight line. How many paths could you make by joining pairs of cabins? So, for example, A to F or B to G. Sorry, my cursor is very hard to see over that white there. There we go. How many different paths can you make? Again, you can pause the video or unpause when you're ready, or go along with me right now. But a lot like the handshake question, we have 7 different cabins, A through G, and to make a path, you're choosing 2 of them. And the path from A to F would be the same as the path from F to A. The order doesn't matter. We would use combinations here, and you can give this a try. 7 choose 2 is 21. There would be 21 different paths you can make. See if you can frame the next variation of this problem in terms of combinations. How many different triangles could you make using these 7 points as the corners? So for example, you can make a triangle between cabins G, B, and C, or you can make a different one between D, B, and C. How many different triangles are possible? You can pause and unpause when you're ready, or follow along. A lot like the last problem, this question is very similar, except instead of making a line, and we need 2 points to make a line, to form a triangle, we need 3 separate corners. So it's just saying how many ways of these 3 cabins can we choose 3 to be the corners of our triangle? Because, and we use combinations because whether we do a triangle from A to B to C or from B to A to C, it would be the same triangle. And the number of ways to choose 3 objects from 7 choose 3 is 35. 35 different triangles we can make. So another kind of interesting application, you'd be surprised how many things you can apply combinations to. We're actually going to revisit an old problem right now. This problem we did in our permutations with non-ordered or identical elements lesson. We did pathway problems. And I'm going to frame them to you in terms of combinations. Maybe you can think of how to frame this in terms of combinations. So we're going from point A to point B. We can only go up and right. We cannot circle back and go down or go left. We want to go directly from A to B. How many different ways can we get there? So we already have found out this answer, but we can get there using combinations too. So pause and think about it if you want, and unpause when you're ready. But here we go. So if you think about it, whether you go up and right, or right, up, there's going to be 4 movements, right? There's going to be 4 moves. 4 moves will get you from A to B, no matter which direction you take. What we're asking here is how many ways, for example, can you choose? Because you got to go up twice, for example. How many ways can you choose of your 4 moves? How many different ways can you choose where your 2 ups are going to be? Like, are they going to be in the middle, or are you going to choose like the first and the last to be your ups? So it's like, of 4 moves, how many ways can you choose the 2 ups? 4 choose 2 is 6. And if you think about how we framed this in our last lesson, we thought of it as you're going to do 2 ups and 2 rights no matter what. And how many ways can you arrange those letters? Well, it's, there was 4 letters, 4 factorial over 2 repeating U's and 2 repeating R's. And that gave us 6 as well. But if you think about it, this calculation is actually the very definition of 4 choose 2, right? 4 factorial. 4 minus 2 is 2 factorial. And finally, 2 factorial. So it's really interesting that these pathway problems can also be framed in terms of combinations. The final one as well. Maybe you want to think about this and pause the video and unpause when you're ready. But to go from A to B in this grid, there's 6 different moves you have to make. You have to move up 3 times and right 3 times. So it's just saying, of our 6 moves, how many different ways can you choose your 3 ups? And 6 choose 3. If you flip back in your notes and look at our answer from the previous day, you'll notice we got 20. But if we want to just refresh our memory with that, it was like, how many ways can you arrange 3 ups and 3 rights? That's 6 factorial divided by the repeating elements, 3 factorial, 3 factorial. And guys, this is just the very definition of 6 choose 3, right? 6 factorial, 6 minus 3 is 3 factorial, and 3 factorial gives us 20. Just as maybe one extra aside, what if, say, in this question, we had just like one more, where's my thing there? There we go. One more block. So it was like we'd have to go up 3 times and write 3 times. There would be 2 ways to frame this question. So there'd be, 7 moves to make. And so you could ask, well, of my 7 moves, how many ways can I choose my 3 ups? But you could also think of it as, well, of my 7 moves, how many ways can I choose to go right 4 times? And you can try it on your own, but 7 choose 3 is the exact same as 7 choose 4. They both give you 35, which is really fascinating, but it's because of the symmetry of this idea of combinations. So we didn't have to necessarily focus on the ups. We could have focused on the rights. And as you can see, you get the same answer either way. All right, guys. So we've looked at combinations, how they're different from permutations. We solved a variety of problems. We tied in the fundamental counting principle. In our next lesson, we'll do some more problem-solving type questions with combinations, kind of ramp things up a little bit. In the meantime, I've, as usual, given you a PDF of lots of practice questions. Sometimes I have not been suggesting specific ones to do. They're all pretty good. In this case, I have. Solutions to all these answers are on the PDF of practice, but I have been recently posting a link to a website that does have full video solutions to most of these problems. And I've done so again today. So I do encourage you to check that out. But I would also love to hear from you and would love to help you with the problem or just to connect. So I hope you guys have a great day, and we'll see you online.